last class we talked about energy method, and I was talking there is a method called unit load method. It is basically derivative of the your unit energy method. So, energy method, if we look in a separate angle, we will get this method which we are trying to define as unit load method. So, it is not a separate method, it is basically energy method, but looking the whole thing is looked in a different angle. Idea is to make the treatment much more systematic or much more mechanical. So, we need not start from the very basic thing. So, energy principle is basically its background, but in a different form we want to apply. Rather, I was trying to explain you here this problem we have solved. M square part we have put there. After taking derivative, we are getting this plus another component. So, this part was basically the moment, and this part is derivative of that moment about that P. Now, if we write here, in general u equal to half integral m square ei dx. So, delta we are trying to tell this is du by dp. It will be this half 2 m dm dp divided by ei dx. Okay. So, u equal to half m square ei dx, where this m was say function of p. Okay. So, p I am writing, it is not the p what we have considered earlier. P may be P, MB or any other quantity, right. So, it is a variable. So, if P is some function of, if M is function of P, so m square by ei dx, this part if we take derivative, so it will be du by dp. So, here this m square will be 2m, 2 it will cancel, it will be m, and this part will be dm by dx ei into dx. Now, this part we can write as, this is capital M, and this derivative part if we write small m divided by ei into dx. Now, you try to go through that expression. So, delta finally we are getting integral m ei dx, capital M, small m, ei dx. Now, you may have, say, take this problem. So, I am keeping both the sheets here, or this I got the earlier sheet, I am putting it here. So, delta, so this is basically m, and this part is small m. What is small m? Derivative of that with respect to p. Now, for that problem, this is basically the m, and this part is derivative of that with respect to p. So, p here it is mb, right. So, if we generalize, so m is what? M is the bending moment generated by the actual loading. Say here at this level, this mb we can drop. So, this is the actual bending moment expression due to the applied load, or here also this part we can drop because x already we have obtained. So, this is due to the actual applied load. So, this capital M is basically the bending moment due to the actual applied load. So we need not bother about taking some artificial load and all those. But what is small m? Small m is derivative of the moment expression with the artificial load and taking derivative about this artificial load. If there is no load there, okay, we are talking in terms of artificial load or pseudo load, something like that. Right. Now try to see the expression of that. Say when it was p and we are taking expression about that. So for p we are getting px and its derivative about p we are getting x. So what is x? Because when you are taking about p, this part will not participate, only effect of, because it is derivative about p, so other force will not be appearing. So it is contribution of the p and we are taking about p. So for moment generated by p, if you take derivative about p, means it is basically if you put a unit load here, so 1 into x will be the derivative. So p there, so moment will be p into x. If you take derivative about p, so px will be x. So what is x? It is basically if you put a unit load there, whatever moment we are supposed to get, that will come. Now from this concept we are coming to unit load method. So it is basically derivative of the energy principle, nothing else. The first component is m, it will be generated by actual load, and second part small m, this is the moment expression generated by unit load, and unit load where we will get, where we want to get the deflection, there we have to put 1 unit load. Say here this cantilever problem, we are interested for finding out the deflection here, there is no load at this point. So just capital M part omega x square by 2 due to the actual load, this is the capital M, because p is 0 here. So it is omega x square by 2 is the bending moment expression for the actual load, and x is what? If we put a unit load here 1 into x, that should be the small m, right. So this small m is due to the unit load applied at the free end where we want to get the deflection, or in that case a slope calculation. If you come at that level, so this part is the bending moment where mb is equal to 0. So this is basically the expression for capital M. Capital M is moment generated by actual load, and this is what? This is the moment if we put a 1 unit moment, so anywhere moment will be 1 unit, so it will be 1. So this is the small m is the moment generated by 1 unit moment at the free end where we want to get the rotation.
So it is just 1 unit?
1 unit, because we are putting some value if you take the derivative, right. So it is p into something, if you take the derivative of that, so p part will be going there, so that will be defined in terms of 1 unit. From there we are trying to define it is a unit load method.